Hello, this is Mr. Wilczewski. Today's lesson is called Advanced Chemicals, or more specifically, how we name and classify chemicals. As you probably know by now, all matter is made up of atoms, and the periodic table contains all the known atoms in the universe. So open up your textbook or find a table online and take a look at the periodic table. It may be a little different than the one in this PowerPoint, but the basic information should be the same. There's a block for each element, and in that block you'll have the symbol for the element, the name of the element, the atomic number, the average atomic mass, and in this case the electron configuration. Now atoms combine to form compounds. Sodium, abbreviated Na, combines with chlorine, abbreviated Cl, to make table salt, also known as sodium chloride. Hydrogen, H, can combine with oxygen, O, to make water, H2O. Now there's we'll talk more about a lot of the compounds later, but now let's take a look at the big picture of the periodic table. There's sections of the periodic table that you need to know that are highlighted here in different colors. Now, you don't memorize the table, but if I were to give you an element and a periodic table without these colorings, you could tell me what section, the name of the section that element is in. So notice hydrogen is all by itself. It's not really in an individual section in this case. It has, we'll talk more about its properties later. The first column here is known as the alkali metals. The second column is the alkaline earth metals. Then this whole section in here in red, including the rows of elements down here, are known as the transition metals. In blue on this side of the table you have the other metals. Then these orange elements here are the metalloids, or semiconductors. They behave like metals sometimes and sometimes like non-metals depending on the conditions. Then these green elements here are the other nonmetals. These brown column here is the halogens, a very important family in the periodic table. And the last column is the noble gases. So for example, if I gave you iron, you should be able to tell me that iron is a transition metal. If I gave you nitrogen, you should be able to tell me nitrogen is a nonmetal. Or silicon right here is a metalloid. Or neon is a noble gas, and so forth. Okay, so let's practice using the periodic table to write the symbols of the following elements. If I said hydrogen, you should be able to look at the periodic table and tell me it's capital H. Oxygen, it's capital O. Sodium, Na. Notice that the first element, the first letter in an element's abbreviation is always capital, and if there's more than one letter, the second letter is always small. Chlorine is Cl. Now let's go the other way around. K. If you see K on a test, you should be able to use your periodic table to know that K is the element potassium. N is nitrogen. Ca is calcium. I is iodine. An important definition, a chemical formula, and that's what this lesson is about, is chemical formulas. A chemical formula includes the symbols of the elements in the compound and the subscripts, those little numbers, that indicate the number of atoms or ions of each element that are combined in that compound. So what is the significance of a chemical formula? Well, a chemical formula tells you the relative numbers of atoms of each kind in a compound. Now, for a molecular compound, the chemical formula reveals the number of atoms of each element contained in a single molecule of the compound. For example, octane is one of the main components of gasoline. That's probably how you got here today, or wherever you are. Octane has the formula C8H18. That means it has 8 carbons and 18 hydrogens. So let's just practice that a little bit. We have the formula H2O. H2O has 2 hydrogen atoms and 1 oxygen atom. Carbon dioxide. Carbon dioxide, CO2, has 1 carbon atom and 2 oxygen atoms. The compound methane, CH4, has 1 carbon and 4 hydrogen atoms. All right, the compound ammonium phosphate, NH4 in parentheses 3, PO4. In this one, it's a little more complicated. Notice the parentheses encapsulates the NH4, and there's a subscript outside that of a 3. That 3 means you have 3 of the ammonium ions, or 3 of the NH4 ions. So that means you have 3 nitrogens, not just 1, and you have 3 times 4, you have 12 hydrogens. So there are 3 nitrogen atoms, there are 12 hydrogen atoms, 1 phosphorus atom, and 4 oxygen atoms. Okay, we're going to cover a number of different ways that we name chemicals. There's 8 ones that are typically taught. There's more than that, but there's 8 ones. We're going to cover in depth 4 of those 8. We're going to talk about common names, ionic names, stock system and oxidation numbers, and the prefix system. Common names. These are the things that people know about because they work with all the time. They have names that everybody in the industry knows. CH3OH is methyl alcohol, and which is it's also known as wood alcohol. It's very poisonous. As little as half a shot glass width is enough to make you blind, and a little bit more will kill you. Ethyl alcohol, isopropyl alcohol, vitamin C, bleach, VX gas, a very deadly gas, DDT, kerosene, caffeine. These are the chemical formulas for these common substances. Table salt, as you know, is NaCl. Here's some more common substances. Methane, which is CH4. If you don't know what methane is, it's used in many homes across this country to heat the home. Here's a short video that'll show you what methane is.
Look at this. New scenes of utter devastation. Thousands of people still stranded, and at this hour, rescuers still scrambling to pull families out of harm's way. Also tonight, a new terror. Can you see that in the water, the bubbling up? That geyser is flammable gas spewing out of a pipe, and it's happening all across one town. A single spark could ignite everything. And the people there can hear the hissing sound as it leaks. Listen. ABC's Terry Moran spent the day in that town, and he's standing by with the very latest for us right now. Terry.
Diane, this is what you see throughout the Jersey Shore right now. Homes just ripped right off their foundations. This was someone's living room. There's a kitchen back there, a bathroom over here. But look down here. None of the infrastructure of the house is left. It's somewhere else. And that is why the real threat here, right up and down the shore, is what you can't see. Fires rage in the town of Mantoloking on the Jersey Shore early this morning, fueled by natural gas. It is a harbinger of a worst-case scenario here, a potential disaster after the disaster. You can smell gas.
You can hear the gas. You can smell the gas. Everywhere you go, you hear shh. Just the gas, all the open gas lines going. They're just scared to death.
Do you hear that? That is the sound that everyone left in these towns is fearing the most right now. It is a hissing gas main. You hear it on street after street right up the shore. You can smell the gas in the air, and fire officials are concerned that these towns are basically ticking time bombs. Everywhere we went along the Jersey Shore today, in town after town, the air was filled with this hissing menace.
If the wind shifts, it's going to get into the crawl space. God forbid a spark.
In the town of Ortley Beach, Frank Mazzo is worried and getting angry. Have you called the gas company about this?
5 times.
What's the response been?
We'll get there as soon as we can.
A high-pressure gas main broke in the floodwaters right next to his home. You can actually see the gas pouring out. It ruptured Monday night.
I don't know why there's not more trucks here right now. I mean, this is where we took the main shot. This is it. Like, where are all these gas trucks? You got down the block, we got down the block. Why can't we get gas trucks down the block?
We saw fleets of earth movers clearing streets choked with acres of sand. Search and rescue teams continue to take the stranded to safety, but only a handful of gas crews. As the air fills with the makings of another catastrophe. ABC News has reached out to New Jersey Natural Gas, that's the utility company here, and received the following response. There is no imminent danger to life or property. People here would disagree.
Okay, that's methane. That's the natural gas we use to heat our homes and cook a lot of our food. Propane, C3H8, that's barbecue gas. Butane, C4H10, it's found in cigarette lighters. And we talked about octane before, C8H18. Alright, enough of common names. There's millions of them. And because there's so many of them, you don't want to be responsible for knowing all of the common names because it's just way too much. Well, we're going to talk about systems of naming compounds where you don't have to know all of the different names, but you have to understand the system, and you have a good periodic table with you. You can name all the ionic compounds. We're also going to let you use charts that list some of the ions. Okay, compounds can be named using the names of the ions which they are composed of. And remember, when writing the formulas for ionic compounds, the sum of the charges on the ions in a compound must total 0. So, monatomic ions. Many elements can gain or lose electrons and form ions. Ions that form a single atom are known as monatomic ions. Ions made up of many atoms are called polyatomic ions. So, for example, sodium can lose one electron. An electron is negative. So when you lose an electron, you end up with a positive charge, a positive 1 charge. This is caused by the excess of protons in the nucleus. Magnesium can lose 2 electrons and form the magnesium ion, and magnesium ion has a +2 charge because it lost 2 electrons. Chlorine can gain 1 electron, and it would then have a -1 charge because remember, electrons are negative. All right, naming positive monatomic ions, that's pretty simple. The positive ions take the same name as the element that it came from. So, for example, potassium forms an ion, and the potassium ion is called the potassium ion. It has a +1 charge. Magnesium with a +2 charge is called the magnesium ion. All right. Now, sometimes these positive ions can have more than 1 charge. That makes things a little bit difficult to keep track of. You have copper that can be a +1 or can be a +2. So we have an ingenious system. We use Roman numerals. So the copper with the +1 charge is called the copper, parentheses, Roman numeral 1 ion, or the copper 1 ion. Copper with a +2 charge on it is called the copper 2 ion. Another way of saying the same thing is that you could say the copper 1 ion has an oxidation number of +1, and the copper 2 ion has an oxidation number of +2. We'll talk more about that later when we talk about oxidation numbers later on in this lesson. All right, the negative ions are a little bit more complicated. The negative ions do not take the same name as the atom, but they take the root name from the atom. And you truncate, you get rid of the ending of the element name, and you add "ide" in its place. So, for example, the fluorine atom forms an ion that has a -1 charge, and we name that fluoride. Drop the "ine" ending, add "ide," and that's the fluoride ion. Or, if you want to be more specific, a negative ion is called an anion. Now, positive is called a cation, by the way. All right, nitrogen forms an ion with a -3 charge. It's called the nitride ion. Here's a list of ions. There should be one in your book similar to this. You'll be for the test, you'll be given a chart of ions just like this. So you don't have to memorize these, but you should practice using them so you can find them quickly. Because you see, they're not really in alphabetical order here. They're in order by their charge. So these are the main group elements and the different positive ions and the negative ions below them. This is not all of them, but it's the more common ones. Okay, so let's practice using this chart. What is the formula for the chloride ion? Well, chloride is down here. You can see it's a -1. Now, what does this look like? Well, if you could shrink yourself down to the size of an atom and look at these ions, they're basically spheres, and the outside of this sphere, this green sphere you're looking at, is an electron cloud. So it'd be a sphere with a -1 charge on it. Alright, some more monatomic ions here. Notice that some of these ions have more than one charge, as we talked about copper before. So let's practice with this. What is the formula for a zinc ion? It's right here. It's Zn plus 2, and it would also look like a sphere with this time a +2 charge. Alright, now notice that some of these ions have more than one charge. Copper can have a +1 charge, we call that copper 1, or it could have a +2 charge, we call that copper 2. Iron can have a +2 charge, we call that iron 2, or a +3 charge, we call that iron 3. Tin can have a charge of +4, we call that tin 4. Tin with a +2 charge is tin 2. Lead with a +4 charge is lead 4. With a +2 charge is lead 2. Now, when we use these Roman numerals in the parentheses, in the examples in the previous slide, to name compounds, that is known as the stock system. The stock system uses those Roman numerals in parentheses. Alright, let's look at the polyatomic ions. These are groups of atoms that are bonded together. We'll talk about how they're bonded when we talk about chemical bonding. But they are bonded together with a covalent bond, and they have a charge on them, which means the net number of electrons and protons is not even, so that it has either a positive or negative charge. Here's some more ions that you need to know. These are typically not listed in the textbook. That's why they're listed here on this slide. Now, let's practice. Write the name of a common polyatomic ion given its formula. So, if you were given this chart, you should be able to tell me NH4 with a +1 charge. What is that stuff? What do we call it? And that's called the ammonium ion. Now, when you visualize this stuff, when you see the formula NH4+, or you see the word ammonium ion, you should try to visualize what it actually is. And here's a picture of this. This is the nitrogen atom, which is colored orange in this case. And these 4 spheres, 1, 2, 3, and 4, are the 4 nitrogens. So it's actually, if you could shrink yourself down to the size of an atom, you'd see this sphere floating in space with the nitrogen in the middle and the 4 hydrogens around the outside, and it has a positive charge on it. Okay, let's look at this. CO3 with a -2 charge. If you saw this on a test and you had this chart, you should be able to quickly identify that as the carbonate ion, right here, the carbonate ion. The carbonate ion looks like this, and this is a moving picture of it, which is more true to life because the molecules are always moving. So you have the carbon in the center, which in this case is blue, and you have the 3 oxygens on the outside. Notice the 3 oxygens are in the same plane as the carbon. That'll be important later on when we talk about molecular geometry. Okay, phosphate ion. If you had to write the name of a phosphate ion for a lab or a chemical equation, you should be able to use this chart to determine that its formula is PO4 with a -3 charge. And it would look something like this. You'd have the phosphorus central in the middle with 4 oxygens. Now it's kind of hard to see the 4. Oh, there you go. You can see 4 right there. Most of the time you can only see 3 at a time, but sometimes you can see that 4th one. Okay. Hydroxide, very important ion in acid-base chemistry. It's OH with a -1 charge. And here's a hydroxide model. Is the oxygen here and the hydrogen attached to it. Carbonate ion, we just did this. Do you remember what its formula is? Or can you find it? All right, CO3 with a -2 charge. And remember, it looks like this. All right, sulfate ion. SO4 with a -2 charge. Notice that this subscript here describes the fact that there's 4 oxygens, but this number here, which is a -2, which is usually written closer to the oxygen as a superscript, tells you the charge on this polyatomic ion. So here we have a picture of sulfate. Here we have a moving picture of sulfate with the sulfur in the middle and 4 oxygens around the outside. All right, here's some more polyatomic ions. If you like these versions of polyatomic ions and they'll help you learn your chemistry or remember your ions, you can go to this website here and see lots of these moving pictures. Okay, now here's where I usually give a quiz to my students. So I'd like you to, obviously I'm not going to collect this quiz from the video, but see if you can get it without looking ahead to the answer. So I'm going to give you clues, and I'm going to ask you from those clues to answer this following question. How do you know how many ions of each kind are in an ionic compound? If all you know is the names of the ions, and you have access to an ion chart, of course. So here's a hint. Study these compounds below and look for the pattern. So zinc ions and chloride ions form a compound. There's our zinc ion. There's our chloride ion. When they form a compound, they form a compound in such a way that there are 2 chlorides and 1 zinc. So we'd write that formula ZnCl2. But why? Why 2? Why 2 chlorides and only 1 zinc? Why not even numbers? Why not 2 and 2? Hopefully you could see the pattern right now. If you can't, that's okay. I'm going to give you 2 more clues. Here's another example. Here's zinc ions and sulfate ions. When they come together, now remember sulfate is already a polyatomic ion, so it has 1 sulfur and 4 oxygens. Its formula is SO4 with a -2 charge. When these 2 things form a compound, 1 zinc combines with 1 sulfate. Not like the one above, not 1 and 2, but 1 and 1. And the formula would be ZnSO4. Why? Well, if you don't know yet, you got 1 more clue here. And you have the ammonium ions and sulfate ions. They also form a compound. And ammonium's NH4 with a +1 charge, excuse me. And so be careful about that. A lot of students make that mistake too. They think that's a +4 charge. That's really a +1 there. And the subscript 4 tells you that there's 4 hydrogens. I'm glad I made that mistake, because hopefully you'll learn from that. Okay. Sulfate ions have 1 sulfur and 4 oxygen and have a -2 charge. When these 2 things come together to make a compound, they come together in such a way that there are not 1 but 2 ammoniums, 1 here, 1 here, and only 1 sulfate. Why? The formula for this is written NH4 in parentheses 2 to indicate that there are 2 of these NH4 things. There's 1 here and 1 here. We put that in parentheses with the 2 subscript outside the parentheses, and only 1 sulfate. Well, if you haven't figured it out already, it's because these come together the way they do so that the charges cancel out, or the charges add up to 0. Look at this first example. -1 plus 2 minus 1 is 0. Same thing in the second example. +2 minus 2 is 0. In the third example, you have +1 minus 2 plus 1 is 0. The charges balance out in ionic compounds. Okay, so let's practice naming chemicals with ionic compounds. You have the compound calcium hydroxide. Calcium has a +2 charge, Ca. Hydroxide is a -1 charge, so you need 2 of the hydroxides. So the correct formula for calcium hydroxide is Ca parentheses OH parentheses 2. right, potassium hydroxide is KOH. Why? Because potassium has a charge of +1, hydroxide is a charge of -1. Now, you can see where you need to have your ion chart handy and need to be able to access it quickly. So I suggest you go through this PowerPoint and practice all of these so you get good at it. Eventually, if you're going to major in chemistry or you're going to work in the industry, you'll know most of these by heart. You could take time to memorize them now. Generally speaking, I would just learn it as you go. That's the current wisdom right now. Alright, so sodium hydrogen carbonate, you've got sodium and you've got hydrogen carbonate, which is a polyatomic ion. Sodium is Na, hydrogen carbonate is HCO3. The sodium has a +1 charge, the hydrogen carbonate has a -1 charge, so you just need one of each. Sodium hydroxide, sodium's Na +1, hydroxide's OH has a -1, so that's the formula for that. Alright, ammonium chloride, hopefully you remember, or you could look it up. Ammonium is NH4, +1 charge. Chloride is Cl, -1 charge. Done deal. That's the formula for that. All right, calcium chloride. Calcium is Ca with a +2 charge. Chloride is Cl with a -1 charge. So you're going to need 2 of these chlorides. Notice you don't need the parentheses here because it's not a polyatomic ion. So the formula for calcium chloride is CaCl2. Lead 2 nitrate. Now, whenever you're using these Roman numerals, we're talking about the stock system of naming compounds. And lead 2 nitrate would be Pb parentheses NO3 parentheses 2. Nitrate is NO3, has a -1 charge. Lead 2 has a charge of +2. Who knew? So you need 2 of the nitrates, so we put that in parentheses with the subscript 2 outside of it. Potassium iodate. Iodate is one of those on the special list I gave you in this PowerPoint. Iodate is IO3, has a -1 charge. Potassium is K, has a +1 charge. So that's the formula. Potassium permanganate. Permanganate's a polyatomic ion. Potassium is K, +1 charge. Permanganate is MnO4 with a -1 charge. Potassium thiocyanate. I suggest you use this PowerPoint as flashcards and use it over and over again until you get really good at naming these. Alright, potassium thiocyanate. Thiocyanate is SCN, -1 charge. Potassium is K with a +1 charge. Sodium ethonate or sodium acetate is CH3COO-Na. Notice usually the positive ion is first in naming compounds. This comes from the organic acetate ion, so it's written differently. When you get into organic chemistry, you'll see a lot of these. All right, so the acetate ion is CH3COO, has a -1 charge. Sodium has a +1 charge. So that's it. It equals 0. That's the whole formula for that. All right, lead 2 chromate. It's PbCrO4. Chromate is CrO4. Lead is Pb. Nickel 2 chlorate. Ni parentheses ClO3. Chlorate is ClO3 with a -1 charge, and nickel has a +2, so we need 2 chlorates for that. Aluminum sulfate. Alright, aluminum has a +3 charge, so we're going to need 2 of those. Why? Because the sulfate has a -2 charge, and the simplest way to get these equal to 0 is to take 2 of the aluminums, because its charge, each one of them has a charge of +3, and if you double that, that's +6. That'll combine with 6 of these sulfates. Each sulfate has a charge of -2, so we need 3 of those to cancel out the +6 charge on the aluminum, because 3 sulfates, each with a -2, would be a total charge of -6. So the formula for aluminum sulfate again is Al2 parentheses SO4 parentheses 3. Zinc fluoride. Zinc is Zn +2 charge. Fluoride is F with a -1 charge. So we'll need 2 of the fluorides. Okay, here's some practice for you. you use these sheets, these PowerPoints, to name your chemical compounds. I'm not going to go through these. I'm going to let you go through these and practice these. Use them like a flashcard. So when we're done with this, watching this video, go to the PowerPoint that's on Blackboard or on the website and practice. Sometimes I assign those assignments. Just check my syllabus to see if, and the lesson schedule to see if I'm assigning them this year. Alright, stock system. More about the stock system. When we use Roman numerals to name compounds, those Roman numerals in parentheses after the positive ions, that's called the stock system. So we're going to write the formulas for chemical names using the stock system. Again, remember, you can use these charts. We're going to write the formula for copper chloride. Now, if I asked you, if you were my lab assistant and I asked you to go into the lab storeroom and get copper chloride, you might come back a little confused, or you might come back with the wrong stuff, because there are two coppers. There's a copper 1, so that means that there's a copper 1 chloride, and then there's a copper 2 chloride. Well, how do we tell these apart? Well, the copper 1 chloride is CuCl, because the copper 1 chloride, the copper in that stuff only has a positive 1 charge, and chlorine has a minus 1 charge. So the correct formula for copper 1 chloride is CuCl2. In copper 2 chloride, the copper has a plus 2 charge. So in order for these ions to add up to 0, there needs to be 2 chlorines. So the formula for copper 2 chloride is CuCl2. Let's take a look at another one. Iron 2 chloride. The formula for iron 2 chloride is FeCl2. The iron has a plus 2 charge. The chloride has a minus 1, so we need 2 of those. Iron 3 chloride, in like manner, would be FeCl3. Now you'd need 3 of the negative 1 chlorides to balance out the positive 3 charge on the iron 3. Alright, tin 2 chloride, another example. SnCl2, tin 2 has a charge of plus 2, the chloride is minus 1, so you need 2 of them. And tin 4 chloride would be SnCl4. Tin 2 oxide. Tin 2 has a charge of plus 2, oxygen. The oxide has a charge of minus 2, so its formula would be SnO. Tin 4 oxide would be SnO2. Lead 2 nitrate. That's Pb, parentheses, NO3, parentheses 2. Lead 2 has a charge of plus 2. The nitrate here is minus 1, so you'll need 2 of those. Alright, writing names from formulas. So here, going backwards a little bit, you have to do a little math. So let's see how this works. Typical test question. Raise your hand if you want to see a test question. Yep, here it is. What is the stock system name for SnO2? Sn is tin. O is oxide. So you look at the charges. Now we know the oxygen is minus 2. And there are 2 of these. So the total negative here multiplies out to be minus 4. That's 2 oxide ions, each with a minus 2 charge, is minus 4. Now tin is one of those things that could have a couple different charges. We don't know which one it is. But we can figure it out because the total charges on this compound have to add up to 0. That means there's only one possibility that all of the tins, and there's only one here, but all of the tins would have to add up to a positive 4 to make this 0. So that's how we figure this out, by knowing that the name for this compound now is tin 4 oxide. Now let's do another example. What is the stock system name for PbCrO4? Now, hopefully, if you've used your reference charts enough for those polyatomic ions, you recognize CrO4 as the chromate ion. So chromate is CrO4, and it has a -2 charge. That's not to say the charge is not on the oxygen, it's on this whole thing, the CrO4. So, and there aren't 4 of these, there's just one of these. The 4 refers to the oxygen only. So, if the charge on the chromate's -2, and it has to add up to 0, then this has to be lead 2. So the name of this compound is lead 2 chromate. Here's another example. There's a typo here. This should read Ni parentheses ClO3 parentheses 2. So how would you name this compound? Well, Ni is nickel, ClO3 is chlorate. The chlorate has a -1 charge, and there's 2 of them. So the total negative of the negative charges is -2. And since it has to add up to 0, there's only one choice for the nickel. This must be nickel 2. So the name of this compound is nickel 2 chlorate. Okay, so stock system using oxidation numbers. Now, oxidation numbers can be used to name non-ionic compounds. So far, when we talk about charges, we're talking about there's an excess of electrons or a deficit of electrons on particular elements, and that gives them a charge. Well, sometimes we can use this concept of oxidation numbers not to mean charge, but it's an artificial way of keeping an inventory of electrons. So keep in mind, a charge on an element will always be an oxidation number, but the oxidation number of a particular element is not always its charge. Okay, so there's some rules here for oxidation numbers. These rules need to be memorized. And I'm going to give a quiz in class, so the next time I see you in class, be prepared to write down these rules in order, just the way that I show them. I'll go through them individually, but then I'll give a final slide that tells you what to memorize. Alright, this first rule, the oxidation number of an atom or ion is equal to its real charge or its assumed charge. Now it's important to remember, as I said, oxidation number is not exactly the same thing as charge. Alright, the next rule, the oxidation number of the atoms in a free or uncombined element is 0. So let's take a look at an example. Here we have NaCl, sodium chloride. Well, the charge on sodium is Na, and the charge on sodium is +1, excuse me, and charge on chlorine or chloride ion is -1. Notice the charges are written as superscripts on this side of the element, and the oxidation number, which I just put in here now, the oxidation number is +1 for sodium. It's written as a larger number in the middle of the element or directly above it. And the oxidation number for chlorine is -1. Here's a case where the charges and the oxidation numbers are the same. Notice that they add up to 0. So that illustrates the first rule, the oxidation number of an atom or ion is equal to its real charge or its assumed charge. Now here's a free element, chlorine, which exists as a diatomic element, Cl2. In this case, both of those chlorine atoms need to add up to 0. And there's only one way you can add up chlorine atoms to 0 and still be the same, because they're 2 identical chlorine atoms, and that's if the charge is a 0 and the oxidation number is a 0. So the oxidation number of atoms in a free or uncombined element is 0. That's here the second rule here. Okay, now let's use this. What is the name for H2O according to the stock system? Of course, you know that as water, but if you were asked on a test to name it using the stock system, you would start with what you know, that the oxygen atom in water is not an ion, but if it were an ion, it would have a -2 charge. That brings us to another rule here. These boxes in red with the white letters are the rules you need to remember. So oxygen is almost always has an oxidation number of -2, except in peroxides, and H2O2 is hydrogen peroxide. In that case, it has a different oxidation number. And in compounds like OF2, we'll talk more about that later. Those are the exceptions, but most of the time, oxygen is a -2. And this is not a peroxide, and you're not combined with fluorine. So in this compound, H2O, it's going to be minus 2. So if the oxidation number is minus 2, and there's only one oxygen here, so the total negative oxidation numbers is multiplies out to be minus 2. And we know that the sum of the oxidation, here's another rule, the sum of the oxidation numbers in a compound or polyatomic ion equals the charge. Well, the charge on this thing is 0, so this has to add up to 0. So that means that the two hydrogen atoms added together has to have an oxidation state of positive 2. Well, since there's 2 of them, that means that each hydrogen would be a plus 1. So the correct name for water in the stock system is hydrogen 1 oxide. Alright, that brings us to another one of the rules. Hydrogen almost always has an oxidation number of plus 1, except when it combines with metals, and then the oxidation number is minus 1. Here's another example. UF6, uranium hexafluoride. Now, this illustrates another rule. Fluorine always has an oxidation number of minus 1. Now, if you didn't know that, it'd be difficult for you to tell us the oxidation numbers or to name this compound. So that's why you need to memorize these oxidation rules. So fluorine always has an oxidation number of minus 1. And since there's 6 fluorides here, the total of the negative oxidation numbers is minus 6. And again, it's a neutral compound, so it adds up to 0. So this must be uranium something fluoride. Must be uranium 6 fluoride. Here's a peroxide compound, H2O2, and the hydrogen atom in a peroxide, it's not an ion, but it'll have an oxidation state of plus 1. Now remember that rule, hydrogen is almost always an oxidation state of plus 1, except in metals when it's minus 1. And so this oxygen here, this is one of the exceptions for oxygen. In order for the total oxidation, positive oxidation state of plus 2 to equal 0 in this compound, the oxygen has to be minus 2, but there's 2 oxygens there. So each oxygen has an oxidation state of minus 1. This is the exception for the oxygen, one of the exceptions. So hydrogen, the name for this compound is hydrogen 1 peroxide. This O2 is peroxide. Okay, so oxygen almost always has an oxidation state of minus 2, except in peroxides like H2O2, where its oxidation number is minus 1. And in compounds like OF, when oxygen combines with fluorine, its oxidation number is plus 2. So here's this example. You know fluorine is always minus 1, and there are 2 of them in this compound. So the total of the negative oxidation states here is minus 2. The oxygen, therefore, has to be plus 2 for this to equal to 0. That's the other exception for oxygen. So the name for this compound is oxygen 2 fluoride. Alright, that's this rule you need to remember. Let's review it again. Oxygen is almost always has an oxidation number of minus 2, except in peroxides like H2O2, where its oxidation number is minus 1. And in compounds like OF, where the oxidation number is plus 2. Okay, KH. What's the stock system name for this? K is potassium, H is hydrogen, so we call it hydride. So potassium is plus 1. Since this has to add up to 0, the hydrogen must be a minus 1. So this is the other exception for hydrogen, or the exception for hydrogen. When it combines with metals, its oxidation state is minus 1. Any other time, the oxidation state of the hydrogen is a plus 1. So the name for this chemical is potassium 1 hydride. Hence the rule, again, hydrogen almost always has an oxidation state of +1, except with metals, then it's -1. Okay, so here's the oxidation rules that I ask you to remember. The oxidation number of an atom or ion is equal to its real charge or its assumed charge. Next, the sum of the oxidation numbers in a compound or polyatomic ion is equal to the charge. Next, in a free or uncombined element such as Cl2, in our example, the oxidation number is 0. Now, some special cases, the oxidation number is equal to the charge of the ion or the pretend charge of the ion, and these you need to remember. Fluorine is always, always, always -1. Oxygen is almost always -2, except with peroxides when it's -1, and in compounds like OF2 where it's +2. And hydrogen is almost always +1, except with metals, then the hydrogen oxidation number is -1. Memorize these. In the next class, I'll give you a blank sheet of paper and ask you to list these just the way they are here. Okay, so let's practice this, naming oxidation numbers. I'm going to leave the rules up here because I'm going to assume you haven't memorized them yet. So refer to these rules. So here's a typical exam question. What is the oxidation number of hydrogen in H2O? Oxygen is -2. Go with what you know. We know oxygen's -2. It's not one of the exceptions for oxygen. So it's going to follow the rule that oxygen is almost always -2. So you can back this up and figure hydrogen out. If this has to equal 0, then both of the hydrogens added together has to be a +2. And since there's 2 of them, each one must be a +1. So the answer to this question, what is the oxidation number of hydrogen in water? The answer is +1. All right, what is the oxidation number of sulfur in SO2? Again, we'll start with the oxygen. We know one oxygen's -2, but there are 2 of them, so that makes for -4. It has to add up to 0, so there's only one choice. This sulfur has to be sulfur 4. So the answer to the question, what is the oxidation number of sulfur in SO2? The answer is +4. All right, what is the oxidation number of tin in tin 4 oxide? Start with the oxygen, which is -2. There are 2 of them, so that makes -4. Because -2 times 2 is -4. And it has to add up to 0, so this tin has to be tin 4. So the answer to the question, what is the oxidation number of tin in tin 4 oxide? The answer is +4. Of course, you could have answered this a lot quicker if you remembered that the number, Roman numeral in parentheses, is the oxidation number for tin in this compound. So you could have just looked at this here and said, well, the answer is +4. Okay, what is the oxidation number of tin 4 oxide? 4. Okay, let's take a look at this. Determine the oxidation number for all the elements in the following compound. All right, so bromine is a halogen, typically has a -1 oxidation number. If you didn't know that, you'd know that you should remember that sodium always has an oxidation number of +1. So sodium with +1 and bromine with -1, there we go. The oxidation numbers are +1 and -1. That's how it equals 0. Okay, I have a special periodic table called periodic table 42, which I'll give you in class, and I'll show you. It has some really cool stuff on it. I'll explain that to you when I give it to you. All right, here's another practice one. NaClO. What is the oxidation number of the elements in this compound? Well, sodium is +1. Sodium is always +1. It's one of the alkali metals. Chlorine is, oxygen is -2. We know that. Now, in this case, chlorine is +1. Now, I know you're used to the chloride ion being a -1. Here's a case where the oxidation number is not directly related to any ion's charges. So the oxidation numbers here for sodium is +1, for chlorine is +1, for the oxygen is minus 2. Okay, what is the oxidation number for the elements in sulfuric acid, H2SO4? We know hydrogen is plus 1 because this is not one of the exceptions for hydrogen. Oxygen is minus 2. So the positives due to hydrogen add up to plus 2 because there's 2 of them at plus 1 each. The oxygens are each minus 2, and there's 4 of those, so that's minus 8. So this looks more like an algebra problem. 2 plus blank minus 8 is equal to 0. Well, this blank is the sulfur, and a little math will tell you it has to be a plus 6. So the oxidation numbers in order: hydrogen's plus 1, sulfur's plus 6, oxygen's minus 2. Determine the oxidation numbers for the element in iodine, I2. Well, this is a free element. It's a diatomic element. Each of these have the same oxidation number, and it has to add up to 0. So the only possible logical choice for that is that they're both 0. The oxidation number of an atom in a free element or uncombined element is 0. Remember that rule? Okay, I'm going to let you do this for practice, and we can talk about the answers in class if you want. Just ask me, and I'll go through it, and I'll put them on the board for you. But write the oxidation numbers for all of the elements in these 3 different compounds. And for the nitric acid, you're going to have to figure out the formula for that. I'm pretty sure you can do that. Or you can click, and you'll see it there. It's the next click. HNO3 is the formula for nitric acid. Okay, practice stock system compounds. Writing formulas. I'm going to let you do these slides for practice. So I'm not going to go through them individually, but you could practice these for homework. All the answers are there. If you can go this fast, you're really doing good. Okay, naming compounds from their formulas. So, let's go in this direction here. You have this compound on a test, and I say, what's the name of this? What's the stock system name for this? So right away you know you're going to be using Roman numerals. So PB, look that up on your chart. PB is lead, and it's got a couple different oxidation numbers, so we're not sure which one it is yet. NO3 is a polyatomic ion, only has one oxidation number. It's minus 1 on the whole thing, because that's the charge on the nitrate. This is called nitrate ion. So you know this compound is going to be a lead nitrate. Well, if you do the math, it has to be a lead 2 nitrate. Why? Because the nitrates have a minus 1 charge. You have to look that up, and there's 2 of them, so that's minus 2. So for this compound to equal 0, it has to be lead 2 nitrate. Here's another compound, PbCrO4. Well, Pb you know is lead. CrO4 is chromate. The chromate has a minus 2 charge on it, so you only need 1 lead. So the formula for lead 2 chromate is right here, PbCrO4, lead 2 chromate. Alright, here you have Fe, which is iron, and SO4, you look that up on your polyatomic ion chart, that's known as sulfate. So this is an iron sulfate, as Fe is iron. And if you do the math, the charge on sulfate, look it up, it's minus 2. For this to add up to 0, the iron compound must be plus 2, so we name this iron 2 sulfate. Alright, ClO3 is chlorate. So this is going to be, and Ni is nickel, so this is going to be a nickel chlorate. So which one is it? Well, the chlorate has a minus 1 charge, and there's 2 chlorates, so that's minus 2. So this has to be nickel 2. Alright, Sn parentheses SO4 parentheses 2. Sn is tin. SO4 is sulfate. Sulfate, look it up, has a minus 2 charge, but there's 2 of them, so that's minus 4. So for this to equal 0, this must be a tin 4 sulfate. Alright, CuSO4. SO4 is sulfate, has a minus 2 charge, so this has to be copper 2 sulfate. Alright, PbCrO4. CrO4 is chromate. has a -2 charge. There's only one lead, so it has to be lead 2 chromate. Ni parentheses ClO3 parentheses 2. We just did this one, but it's worth reviewing. So we have, this is a nickel. Ni is nickel. ClO3 is chlorate. So it's a nickel chlorate. The chlorate has a -1 charge, but there's 2 of them. So that means that nickel has to be a nickel 2 chlorate. Aluminum sulfate, Al2SO4 in parentheses 3. Now aluminum has a charge of +3. Sulfate has a charge of -2. So this balances out to 0. And aluminum only has 1 possible charge. So even though this is technically the stock system, you don't need Roman numerals if the positive ion only has 1 choice for charges. Okay, this is more at-home student practice. So I'll let you go through this slide at your own pace. All right, now here's a practice quiz. What is the oxidation number for all of these elements? Fluorine in all compounds, -1. Oxygen in most compounds, the rule says -2. Oxygen in this hydrogen peroxide, H2O2, well, that's an exception for oxygen. So the answer is -1 there. Oxygen in CO2 is not an exception, so it's the normal -2. Hydrogen compounds containing metals, that's a -1. That's the exception for hydrogen. Hydrogen in KH, well, K is a potassium, which is a metal, so this is the same thing as the one above it. This is hydrogen combining with a metal. The oxidation number is -1. Hydrogen in water, the oxidation state is +1. What is the oxidation number in any pure element? Well, it's 0. What is the algebraic sum of the oxidation numbers of all atoms in a compound? That's 0. What is the algebraic sum of the oxidation numbers of all atoms in a polyatomic ion? Well, it's equal to the charge. What's the oxidation number of sulfur and SO2? It's +4. Of sulfur and H2SO4 is +6. And of tin and tin 4 oxide is +4. So practice these, use these as a flashcard. Expect to have a quiz like this in class. Matter of fact, the quiz might look something like this, or typically I like to rearrange the order of things so it's a little bit different. Alright, but that would be a quiz. Practice on both of these. Okay, so that's just a note for me. Alright, so let's talk about the prefix system. Here's a chart of prefixes. You're probably very familiar with this. You have compounds like carbon monoxide, and the mon tells you there's 1 oxygen in carbon monoxide. You have another compound called carbon dioxide, and that's what that di means, 2. The mono means 1, the di means 2, tri means 3, tetra means 4, penta means 5, hexa 6, hepta 7, octa 8, like octane, nona 9, deca 10, like there's 10 years in a decade. Alright, so let's practice this. Carbon dioxide, 1 carbon. Notice we don't have to say monocarbon for the first one. If it's the first element and there's just 1, you just say carbon. So this is carbon dioxide. The formula is CO2. Carbon monoxide, the formula is CO. Sulfur dioxide, the formula is SO2. Sulfur trioxide is SO3. If I'm going too fast for you, just pause the video wherever you want and while you figure out the answer, or use the PowerPoint that's online. Alright, sulfur tetrachloride, tetra, remember, means 4, so that's SCl4. And silicon dioxide is SiO2. Antimony pentachloride is SbCl5. Carbon tetrafluoride is CF4. Dinitrogen trioxide, 2 nitrogens and 3 oxygens, is N2O3. Alright, let's go the other way. CF4 is 1 carbon, so it's carbon, and 4 fluorides, so it's tetrafluoride, carbon tetrafluoride. SiO2 is silicon dioxide. N2O3 is dinitrogen trioxide. Now let's talk about acids. All right. Acid is a certain type of molecular compound. We'll talk more specifically about that later. And most acids that are used in the laboratory are either binary acids or oxyacids. Binary acids contain only two elements, and they're usually hydrogen and a halogen. And oxyacids contain hydrogen, oxygen, and a third element, usually a nonmetal. So many of your polyatomic ions are produced by the loss of hydrogen ions from oxyacid. So here's an oxyacid, sulfuric acid. If you lose these hydrogen atoms, look what you get. You get SO4, which is the sulfate ion. Nitric acid, HNO3, the nitrate ion comes from this. A phosphate ion comes from phosphoric acid. And a binary acid is an acid that contains only two different elements, hydrogen and an element like fluorine, chlorine, bromine, or iodine. So your binary acids typically are HF, which is hydrogen fluoride, HCl, which is hydrochloric acid. HF is also called hydrofluoric acid. HBr is hydrobromic acid, and HI hydro. So notice how these things are named. The name of the binary acid begins with the prefix hydro, followed by the root name of the second element in the prefix, and then ending in the word ic. So here they are. We have hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, hydrosulfuric acid. All right. Some practice using that chart. Could you name these compounds? Hydrochloric acid, HCl. Hydrobromic acid, HBr. Hydroiodic acid, HI. Hydrofluoric acid, HF. Hydrosulfuric acid, H2S. Okay, an oxyacid is an acid that contains a compound of hydrogen, oxygen, and a third element, which is usually a nonmetal. So here's some of your oxyacids. HNO3, which is nitric acid. H2SO4, which is sulfuric acid. These oxyacids do follow a pattern. I'll leave it to you to see if you could figure out this particular pattern. But here's some of the common oxyacids that you should know. In my test, I'll give you the chart to refer to these acids if I'm asking you about them. Okay, practice naming oxyacids. Phosphoric acid, H3PO4. Sulfuric acid, H2SO4. These are the more common acids. You should be able to know the names of these acids off the top of your head if you're going to look smart in chemistry lab. Nitric acid, HNO3. All right, some important bases. Bases are the opposites of an acid. We'll talk about their chemical properties later on. But ammonium is a base, NH4. Calcium hydroxide is a base, Ca, parentheses, OH, parentheses 2. Potassium hydroxide is a base, KOH. Sodium hydrogen carbonate, NaHCO3. Sodium hydroxide, NaOH. Sodium carbonate, Na2CO3. Alright, some organic compounds. We're not going to spend a whole lot of time on this. You'll have a whole course later on. If you're going on to chemistry or something that needs a lot of chemistry, you'll have organic chemistry. Methane is CH4. Ethane, C2H6. Propane, C3H8. Butane, C4H10. Hopefully you see there's a pattern here. Pentane is C5H12. Hexane is C6H14. Heptane, C7H16. And octane, C8H18. Methyl alcohol, CH3OH. That's wood alcohol, very poisonous. Ethyl alcohol, this is the stuff that's in drinking alcohol. This can also be very poisonous in the wrong amounts. C2H5OH. Okay, here's a little matching test here. Based on what we've talked about so far, match each chemical to one of the listed chemical types. NaOH. Hopefully you remember that's B, a base. C3H8, hopefully you remember that's propane, which is an organic compound. Answer C. HNO3, we just talked about that a little bit a while ago. That's nitric acid. Hopefully you'll recognize that as an acid. HCl, that's another, that should be a small case L, by the way, another typo, sorry about that. So HCl should be in the acid group, answer A. Ca, parentheses, OH, parentheses 2 is a base, it's calcium hydroxide. CH4 is methane, you saw a video about methane, that is an organic compound. And barium chloride, one of barium's ionic compounds. Alright. Okay, so here's another matching practice quiz for you. Match each chemical to the chemical that is most like it. Select the chemical that might possibly be substituted for the first chemical in a chemical reaction. Here's my disclaimer, never make chemical substitutions in lab without permission of your lab instructor. Alright, NaOH. Hopefully you remember that's a base. So which one of these is also a base? Well, the answer is C, calcium hydroxide. C3H8 is an organic compound, that's propane. And the only other organic compound in here is CH4, methane, so you should have matched that to B. HCl is hydrochloric acid, and you'll match that to HNO3 here, which is nitric acid. Okay, I'm going to give you a homework assignment. So every day, every single day, for 10 minutes, for 3 weeks duration, practice naming compounds using the below slides. All right, this PowerPoint is also found online, and you can just use it as a flashcards. All right, that's the end of this lesson.